Hello and welcome to the next episode of the Klingberg Wing Mark II development. I'm Klingberg, your host. Today we have a very important topic, and I can't emphasize that enough. It has to do with the controllability and stability of swept flying wings. In fact, it could be a serious topic if you're developing a man-carrying flying wing that's swept. The information that I'm about to present in this video could mean the difference between a successful aircraft and one that proceeds to destroy itself and perhaps the person who's flying it. This is an age-old problem with flying wings, and people have been working on it for a long time, and my recent tests showed some very important characteristics of control surfaces that everybody that's involved with designing flying wings should know. So, without further ado, let's just dive right in. As you may recall, my Klingberg Wing Mark II is my second flying wing, and my first one had a nasty problem with stall spin. In fact, that's what caused the loss of the aircraft. And the fact that we didn't kill the test pilot in the process was a miracle. So stall spin problem, big deal. Many people have lost their lives to this problem on flying wings. And I set about designing my second flying wing with the paramount goal of being spin resistant or hopefully even spin proof. Of course, nothing's absolutely spin proof, but spin proof within the recommended CG ranges. And much of the work that I've been doing on this wing has been driven by make it safe to fly. And in the process, I've discovered that the shape of the elevons is critical to the issue. And what's at play here, and let me get my little whiteboard here for a second. We'll get this, and then we'll move on later. We got to remember at all times that span-wise flow promotes stalls and spins. The span-wise flow is caused by several factors, but it's just inherent in swept wings, especially swept tapered wings, which pretty much defines a swept flying wing. Most of them are tapered. Like the Swift has a small amount of taper, Millennium has a small amount of taper. Some have much, much more. A lot of the Horton designs have a lot of taper to them. And the amount of taper makes a difference, and the shape of the elevons makes a big difference. But we want to prevent span-wise flow. And as you know, I've been working extensively to do that. And so far, what I've done, as you know, is I've moved the winglets inboard, and that winglet acts as a large potential fence to keep the flow going straight and not go span-wise. Fences, as you may recall from previous videos, fences are not an effective solution, because fences deal with the boundary layer, and this is a problem with the potential flow field, not the boundary layer. What happens is the potential flow field gets going span-wise, creates a shearing force, pulls the boundary layer sideways across the wing, and you get a premature stall. So we want to stop that as much as we can. And the inboard winglets have gone a long ways towards that. Another way of preventing span-wise flow or preventing aggravation of span-wise flow is to not have control surfaces there. Control surfaces, depending upon the shape, can really aggravate the amount of span-wise flow. And I'm going to talk about that in a minute and show you some video. The Mitchell wing is an excellent example of don't put control surfaces on your wingtips, or actually don't have the wing itself be a control surface. The Mitchell wing has control surfaces out at the wingtips. However, they are detached and stepped down elevons. In other words, there's a gap between the wing and the elevon is a full flying wing up and down. Now, that can be an excellent solution, makes the glider easier to build. It can be a little bit heavier. It's a lot draggier though. And word has it that the Mitchell wing still had some nasty spin tendencies if you got the CG a little too far aft. In fact, somebody related to me once that they were stuck in a spin in a Mitchell wing for a while, and they were just glued up to the side of the pilot's cage, and they weren't sure they were going to get out of it, but they did. They were lucky. Got to get that CG forward, and don't fly it that slow again. So I went down the path of not having control surfaces out on my wingtips, and on the model it worked wonderfully. No matter what you did to it, you really had to force a spin, get the CG aft and force a spin to get it to spin. Other than that, it was very benign. And as we've seen on the full-size glider, the 6 flights that I've had it on, I've mentioned before, I've probably stalled it 5 times in those 6 flights, and it doesn't drop a wing. It just kind of parachutes down to the ground in kind of a deep stall situation, but it doesn't drop a wing because those wingtips are always flying. But as we've come to learn, I wasn't surprised that the inboard elevons are just not effective enough to control the glider, and I've had to extend the elevons out towards the wingtip. In fact, almost all the way out to the end. And recent tests show that that's very effective. I now have doubled, maybe a little bit more than double my control effectiveness, and it's working quite well. And recent ground tests show that the flow is in pretty good shape, but it could be better. Still getting a little bit of span-wise flow. So I did a series of tests with just full-scale mock-ups of the wingtip panel, and I have those behind me here, and I'm going to talk about them in a minute. I'm testing different elevon shapes and looking at the flow conditions and looking at what minimizes the span-wise flow. And I'm using some of the experience that I have, and I'm gathering information from others and blending it together, and discovered something very interesting along the way. And when we get down to the end of the video, maybe 2/3 of the way in, you'll see that phenomena and what causes it and why the shape of the elevon on a swept flying wing is really critical. So let's move along to the 3 samples that I have, and we're going to take little breaks in between so I can run video for you of the tests that were done on those 3 samples. Okay, here we are with sample number 1 of the elevon shape. This is pretty much a standard control surface shape. It's a certain percentage of the chord of the wing. This is a full-size mock-up of my wingtip panel outboard of the winglet. Yeah, it's a flat plate airfoil, but for what we're doing here, that's good enough. I was going to build wing sections just for this test. It's good at low angles of attack, and we can study the flow conditions relative to the control surfaces, even with a flat plate. So let's not worry about the lack of airfoil. So, because the wing is tapered, this elevon, being a set percentage of chord, is wider at the root than it is at the tip. Get this narrower root wider. So, when you deflect it up like this, you're presenting to the relative wind coming in a wall, a fence of sorts, and because it's tapered this way, you're just encouraging the wind to go this way. It's easier, and I'm going to explain to you in a minute why it's easier for the air to just turn and go out along the elevon. And I'm going to run you a little bit of video here that shows you this under test, and you'll see these tufts. When this comes up like this, you'll see these tufts go out span-wise. And for gliders, this is a really big problem because gliders fly slow a lot of the time and in a turn called thermaling. Sometimes we do some ridge turns really slow also. And quite often in that maneuvering, to adjust our speed, we have to move the elevons a little bit. And sometimes we move them up. And you might be flying just fine, flow's attached. You know, these guys are going straight back like this, everything's cool, right? And then you deflect it a little bit more up and out they go this way. These guys start to follow it, and before you know it, you got a whole bunch of span-wise flow, put some shear into the boundary layer, and you get premature stall. When you have this type of elevon on just about any flying wing, as you're in a slow turn like this, if you tweak that elevator up just a little bit too much, It's amazing how fast they break into a spin. It's almost like the inboard wing just stops, drops, goes backwards, and down you go. I've never had to ride through that, but I've had it happen on a lot of models. It's pretty scary. It's bad. So this type of elevon shape causes all kinds of problems. Now let me run a little bit of video for you here and watch these tufts as I deflect up and down on the elevon, and watch how they go out spanwise. Now you will see them going spanwise when it's down, but that is a separated flow condition, separate problem from what we're talking about right now. That is also a problem that I'm working on. We're going to discuss that later. But right now, in this case, we're concerned about the up elevon situation, as though you're flying very slow and a turn and your elevons are up like this. So let's roll that video.
Oh yeah.
Before the wingtips start to go spanwise. And as soon as I put this up, you can see how they go?
Yep.
That's the compressible flow for you, right? Okay, did we get all of that?
Yes.
Okay, so let's put this wing shape.
Okay, welcome back. I hope you were able to see how these tufts are going out spanwise like this. We don't like that. We need to put a stop to it. So, I know from my previous work with models that barn door elevons can work pretty good sometimes. Here we have an example of that. A barn door elevon is generally a large percentage of chord, somewhere around 25%, 30% of chord, sometimes even more. The Horton brothers were working on elevon shape also, and I'll put up a picture here of their foot launch version in Argentina, where you'll see that their barn door elevon goes way up like this, up to the spar and back, and it's got a very short span on it, but a huge chord. I don't know if they're working with the same phenomena that I've been looking at here, but it's clear that they were working on solutions to this spanwise flow problem. In fact, they actually had a cargo version of one of their flying wings that had the winglets inboard. Put a picture of that up too. Because they had experienced problems with their, I think it was their Horton 3 or Horton 4 had nasty spin problems, and one of their fatal crashes, I believe, was due to stall spin. So, barn doors. They can work pretty good on models, and I thought about using them on my current wing design, and I tested it out on various versions of models of mine, and found sometimes it works, sometimes it doesn't. And it wasn't particularly clear why one worked over another design. But when they do work, they really help stop the spanwise flow. These guys, instead of being way out like this, they'll be a little less, somewhere around in here. And I'll run some video here, and you can watch this particular version. The constant chord on the elevon and a significant percentage of the chord of the wing. So that means the percentage of chord of the elevon out here at the tip is more than it is here at the roof, because the elevon is a constant chord along its length. So let's take a look at that video. Welcome back. I hope you had a chance to see that there's some differences, but they're really minor. This particular style of barn door elevon didn't solve the problem. Still had significant amount of spanwise flow. A little bit less, but still significant. Still a problem. And the question becomes, why? Well, why is this not working? I've seen it work on some models. Why is it not working now? Well, I'm about to show you what does work. So, as you may recall, in my in my work on my wing, I worked a lot on the stall spin problem, and I approached it from washout. What is the effect on the washout of the wing? It's essentially effective washout when you move the elevons. You move the elevons up and down, you're changing the washout in the wing. And I have a whole series of 7 videos on the whole stall spin problem, and in there I actually physically show how the washout of the wing changes with different shapes of elevon. If it's tapered one way or a barn door or a reverse taper, they all have a different impact on the amount of washout in the wing. And I developed a little spreadsheet which you can get over on Patreon. You can get a copy of that for free, and it tells you how to shape your elevon to prevent stalls and spins based on various parameters of a given wing. The amount of taper in it, the size of the elevon, shape of the elevon, how much washout do you have in it, so forth and so on. And I ended up with what I call the reverse taper elevon, and it flies really nice. I've had no issues with it whatsoever, and I was absolutely certain it was strictly a washout effect. But as it turns out, that's only part of the answer. There's actually 3 parts to the answer. One is having to do with washout. One is having to do with just the mechanical interaction of the elevon with the airflow. And the other one has to do with an aspect of fluid flow that we hardly ever talk about. It's a complex topic, and I'm going to go into it in a little bit of detail here in a few minutes. But here is the 3rd shape that I tested. I hope this is in view here. And you'll see it has a huge reverse taper. The elevon has a very narrow chord here at the root and a really wide chord out here at the tip. In fact, the elevon at the tip comes all the way up to where the spar would be on my wing. This is where the spar is, right here. And the elevon at the tip is at the spar. So, huge reverse taper. In fact, this hinge line is not quite, but almost perpendicular to the incoming flow. Close to it. Not quite. The results were fascinating. Here's what happens. For deflections where separation starts to occur going down, yeah, we get the separated flow here, and these guys go out like this, and we still see a little bit of that out here on these tufts, but not these guys up here. So the elevon's down like this, and these guys are still going straight, and these guys are starting to go out towards the tip. Well, that's an improvement. At least we have a portion of the elevon that the flow is staying attached, not separating. And if you've been watching my videos, you know I went through a series of design changes on my wing. Lumps, sealing the gap, making the elevon taller than the main wing panel, all kinds of stuff to try to energize the flow. Oh, yeah, even trip strips and turbulators, Vorlons. Man, I've tried everything. And I would get small increases, 10, 15%, more deflection available to me before it's separated, but not like this. This is, I got a good chunk of the elevon, flow is straight before it goes off the end. And even more amazing, in the up configuration, these guys are going out span-wise here at the root, but these guys out at the tip, straight up like this. They got some wiggles in them, flows struggling a little, but they're all straight like this. It's like, wow, that's amazing. How is it that the flow here is going span-wise, but somehow this stuff is still going straight out here? And it really boggled my mind, and I'm going to run that video for you right now so you can see it for yourself. Okay, welcome back. Wasn't that amazing to see? The shape of the elevon completely changed the flow conditions out here in the tip region and just stopped the span-wise flow for large deflections up like this. That's exactly what we want. That's pretty cool. But how does it work? Well, I had to think about it for a few days. You can go to school for many years, you can get your master's degree in aero engineering, you can be a pilot for decades, you can have hundreds of designs under your belt, and sometimes you're still perplexed. You go, oh, how is that possible? What is it about the change in the shape of the elevon that would cause those guys to stay attached like that? Like, wow, a little miracle. So I ran it through my brain and I ground on it for several days. And then I finally came up with the answer. And it's a topic that we don't talk about much. It's taught in school, and it's a very basic thing having to do with fluid dynamics, and that's called momentum. And what happens on an airfoil? Let me get this back over here. This is the airfoil that I'm using on my wing. It's a 23. I use the 23015 and the 23012 in various spots along the wing. I think this is the 23012 here. And this is the pressure distribution on that airfoil. And this is the pressure distribution on the top of the airfoil, and the black line is the pressure distribution on the lower surface of the airfoil. And you can, if you understand pressure distributions in airfoils, you can see why I chose this airfoil. The peak of the low pressure is way up here by the nose. It's like in the first 10% of the airfoil. What that means is that the majority of your lift, the lift center of this airfoil, is far forward. And that's what gives it the nice neutral pitching moment that we want for flying wings. That and just a whisper of reflex on the mean camber line. In fact, the reflex is so small you can't even see it on the outside of the wing. It's just on the mean camber line. So that's why I chose this airfoil. High L over D, and it has a very benign pitching moment because it's what we call front loaded. Okay, so and please remember on these plots, this is negative in this direction. This is minus. This is lower and lower and lower pressure is going up, and plus goes down. I know that's reverse of most graphics, but for airfoils, that's how we plot it because visually it makes a little more sense to us. Okay, so here we go. The air comes in, zoom, the pressure drops as it accelerates up over the leading edge of the wing. And remember from Bernoulli's principle, as the flow accelerates, the pressure drops. And that's what we have here, pressure dropping, pressure dropping. And then it gets here to about, let's see, what is that? That's about 15% of chord. And the pressure starts to increase again. Now that's because the air has gone over most of the curvature of the wing already, and it's starting to go into a portion of the airfoil that's not curving up as rapidly. Doesn't have as much curvature to it. In fact, right here at 30% of chord is the maximum thickness point of this airfoil. And that's where the pressure recovery begins. So all of this pressure that was dropped down starting to come back, and then at this point the flow starts slowing up. So accelerating, 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 no longer accelerating, now decelerating. So this is kind of a coast phase. And what you can equate this to, I'll do a cheap analogy here of a guy on a bicycle trying to get up a hill. Now, we made it a rule in his little race that he can pedal as hard as he wants, he goes as fast as he wants until he gets to here, and then he has to coast. Because that's what's happening on the airflow. That flow is accelerating, accelerating, accelerating until you get to the maximum thickness point of the airflow, and then it has to begin to slow down. Remember, the flow wants to go back to its original speed and pressure when it gets to the trailing edge. Doesn't always happen. It's not required that the flow be going zero when it gets to the trailing edge, but that's where it wants to be. Most airfoils, you still have some speed when you hit the trailing edge, and that's why you have turbulence behind the wing and some added drag. So the guy's riding along here, and he starts up the hill, and he begins to coast. And if he had enough speed with him to start with, he can coast all the way up here until he hits the finish line right here, and he's done. That's pretty cool. He can coast through a portion of the race. But what happens if we deflect the control surface? Well, let's take part of this guy off and say, oh, I just put up a control surface. Oh, he's still riding as hard as he can. He starts coasting here, he's doing fine, and all of a sudden, this wall's in his way. He needs more energy to get up this hill, but we're not going to let him pedal. So he's coasting, and he loses speed really, really fast. Where's he going to go? Remember, if this were airflow, there's a bunch more bicycles right behind him. You got all these air molecules backing in, backing in, backing in. He can't roll backwards down the hill. There's a whole bunch of guys behind him going, get going, get going, get out of the way, get out of the way, get out of the way. His easiest way to get out of the way is to go spanwise. Because that's where the wingtip is, that's where his neutral pressure situation is, and he's got a whole bunch of other air molecules inboard that are also trying to go out to the wingtip. So you stick up a control surface like this, and the air's coming along, and it can't get up that hill. There wasn't enough speed stored up here to get him past us. If it's a little deflection, oh yeah, he might make it. But if it's enough deflection, he can't get up and over that hill because he has insufficient momentum. Remember, momentum is mass times velocity. So he has a set velocity here and he has a set mass. So he's only going to go just so far, and that's it. Now, when we add turbulators, or when we make a lump on the elevon, or when we make the elevon thicker than the main wing area, what we're doing is we're forcing the flow to re-accelerate to try to keep it attached to that control surface. And it works to a certain amount, 10% or whatever, but that wasn't enough for my solution. So here we have a situation where deflecting the control surface will force it upward, will force spanwise flow, and that's bad. But it didn't happen for the reverse taper elevon. And why is that? Well, it's pretty interesting to think about it. Let me bring that back up here. Let me sit this down here and bring up that other link there. So here's the heavily reversed elevon, heavy reverse taper. Now remember, I showed you in the plot of the airfoil that the lowest pressure is at about 10% of chord, 15% of chord. And the lowest pressure is at 15% of chord. The maximum velocity of the flow is at 30% of the chord. The maximum velocity that the flow gets to is at the maximum thickness of the airfoil. And on this airfoil, this wing, that's 30% of chord. Oh, look where the hinge line is. There's our answer. This hinge line here is at 30% of chord from the leading edge. This spot right here on the wing, is the maximum speed that the airflow gets to going over this airfoil. From this point aft, it's decelerating. From this point to here, it's accelerating. So, maximum thickness of point of the airfoil is where there's the maximum velocity and hence the maximum momentum. Well, if we need momentum to get up this hill, better start here. If we put a little strip elevon back here, there's no momentum left to get up over the hill of the control surface deflected up. This is a situation of positioning the elevon or shaping the elevon such that the hinge line where the air molecules have to start going uphill is where the air molecules are moving the fastest and have the highest momentum and hence the highest probability of getting to the trailing edge without separating or going spanwise. And that's why on this elevon inboard we got spanwise flow, because way back here away from the leading edge, when you're way back here away from the leading edge, your momentum's really low. You've lost a lot of velocity. You no longer have enough momentum to get up the hill. Out here, you got plenty of speed, plenty of momentum, and you can get up this hill. Now, you may have noticed in the video that these wiggle around a little like this, and the flow is struggling to get up this huge hill because the deflections are large. They're up around 30, 35 degrees. It's a lot for the airflow to get up over. But that explains it. So, I told you there were three things that work here. So, we know one of them has to do with the change in washout on the wing or the shape of the elevation. So reverse taper gives you better washout at the wingtip, which is a good thing for stopping spanwise flow. We now understand that if we put the hinge line where the momentum of the flow is the highest, it has the highest probability of getting straight up over the control surface without separating or going spanwise. Likewise, when it goes down, when you go down, that's why we have straight flow for this much, and then it starts to go spanwise, because you're asking the flow to turn a corner when it has plenty of energy in it, the momentum, to get around the corner and continue on its straight path. So that's why it works both down and up. And then there's another factor, and that's just strictly a mechanical one. So we have this swept wing like this, and this air is coming in on these streamlines like this. And if I am perpendicular, if my hinge line is perpendicular than that, and the airflow is coming in, and it goes like this, and it goes, oh, which way do I go? Well, it doesn't make much difference, does it? Well, in this case, the wing's tapered, so a little easier to go that way. A straight wing, I'm not sure what would happen. But this is just strictly a mechanical thing where the airflow has to decide which way is easiest out for me, because I can't get up this hill. So if we make this perpendicular to the airflow, it helps keep the airflow aligned with the streamline. If this is highly tapered the other way, like the first one that I showed you where it's really tapered, well, you're putting up a wall here like this. Here, I'll use my whiteboard. So here's my control surface. I put up a control surface like this that's tapered the other direction. Oh, that's, the air comes in and goes, oh, you just told me which way to go. You want me to go that way. Because there's a wall here that's pointed off that way. So that's why tapered elevons, standard control surface shapes being a percentage of chord of the wing, are really bad. Because they're tapered, going out like this, if it's a tapered wing. And it just shoves the flow off the wingtip. So that's the three factors that are at work. One, just the mechanics of where the hinge line is relative to the flow, and whether you're shoving the flow off the tip or whether you're just kind of stalling it in place. We have the washout factor, and then we have the momentum factor. You need to get all three of them working together to ensure that the flow stays attached for as long as possible and you minimize your spanwise flow. Now, here's the types of elevons that you can see on flying wings sometimes. This is what I had on my original flying wing. I had essentially a strip elevon, 6 inches wide, entire span. This is what I like to call, here, I'll write it down here. Yep. It's a death trap. It's really bad. The strip elevons are horrid for flying wings, for swept, tapered flying wings. This is a sure way to an early grave. My original wing, without provocation, at the slightest hint, would break into a spin. I'll put up a picture here of ground testing it, and look at the tufts. When I have the elevon up, the tufts get to the hinge line in the elevon, turn 90 degrees, and go out along the span. Horrible situation. So, that's a death trap. Don't do it. Never, ever put strip elevons on a tapered flying wing, swept flying wing. Really bad. You'll lose your model or kill yourself. Pick one. Okay. We saw this one in the video, the set percentage of chord, and we saw how bad that was. You deflect this up and down, and this flow back here just goes like this. It goes out spanwise as soon as you deflect it up. This is also a death trap. We'll just call it DT. This is a death trap. This is bad. Horton had this on their early designs. It was the Horton 3 or Horton 4. I'll put up a picture of it here. Its demise. It's an ugly crash. Killed the pilot. And many other flying wings have had elevons like this. There's a Turkish one that had these. They lost that to a stall spin accident. Killed the pilot. So, the death trap. Don't ever put tapered elevons on your flying wing. A set percentage of chord. Okay, so this is a death trap. Don't do it. Many others have done it. You'll see it in a lot of pictures. Bad. It's killed a lot of people. Okay, then we have barn door elevon. Well, let's see. That's been on the Swift. The Hortons tried it. Northrop had them, and many others. Some of these are great gliders or great aircraft. Some are not. And it's this, when is the barn door the right solution? Well, we know one of the secrets now. It has to do with momentum. You have to have this thing have a large enough chord this way so you're up into the area of maximum flow velocity or higher flow velocity. You have to get up here at some point where the air still has enough momentum in it to get up over the control surface at its maximum deflection, or around the corner and down the control surface. Where is that point? Where is it? Can we do a calculation that says, oh, I have enough momentum in my flow to get up this hill when it's deflected at 30 degrees? Well, I have kind of a small whiteboard here, and I'm not going to torture you by putting up the Navier-Stokes equations, because that's what you have to actually solve to answer that problem. And by the way, if you have the solution to the Navier-Stokes equations, drop me a line, because I think there's some math awards for you out there somewhere. They're essentially, for this type of situation, they're unsolvable. This is one of those things that we'd have to go in a wind tunnel for a particular design and measure. Go out and fly it very, very safely. Until we find out, oh, that's enough of chord, the flow has enough momentum, and I can get up over that thing. The Swift is an excellent design, very safe, worked out well for them. Northrop, on the other hand, had sort of barn door elevons, but in terms of percentage of chord, not nearly as much. We know what happened in a Northrop wing. You'll hear lots of people say, oh, it was caused by this, it tumbled, that, and the other thing. When the Northrop flying wing went in, they were testing aft CG locations. That's a known fact. And if you're testing aft CG locations and you're flying slow and you deflect your elevon up, well, I think we now understand you could have a problem on your hands. And considering how that thing came apart in flight, it's my guess it was in a spin. They got the nose down, they were recovering from the spin, and they did a pull-up, and that thing was only rated for utility-type loads, 3.5, 4 Gs, something like that, and they just exceeded the G limit and ripped it apart. So, barn door elevons. Sometimes they work, sometimes they don't. So, what do I think of them? Avoid them if you can. If you have a choice, avoid the barn door elevon. So, our best answer, our winner, the winner, is the reverse taper elevon. Because of the three factors, this really helps keep the flow attached. Now, how much reverse taper? Well, I have an answer in my spreadsheet in terms of washout, but I don't have an answer in terms of momentum. Haven't figured that one out yet. Haven't been able to test for it. But the Prano, the D and the M versions, that would be the half-scale model and the man-carrying aircraft, used a reverse taper elevon, and I'll try to find a picture and put it up here. And I know that the half-scale model flew really well, and the man-carrying one flew under tow, but I've never seen any footage of it in free flight, so I'm not sure whether this reverse taper elevon was proven out or not. this reverse taper is now being used on a bunch of models. I get another picture up here, both commercial and plans for flying wings that use this reverse taper, and they all fly really well. And we know that the Prano half-scale flew well. We know that my model flies well with reverse taper. And we're getting an inkling with my full-size wing that this is going to work. In fact, from these flow tests that I just did, we see that this elevon extension out to my wingtips to where my elevon is all the way up to the spar, it's probably going to work out just fine because we're in the flow field of maximum momentum, and I'll be able to do large controlled deflections without having issues with separating the flow or causing a lot of spanwise flow. And the Millennium, for different reasons, Steve Morse on the Millennium designed those elevons to reduce the induced drag, but as a consequence, you actually help prevent spins with that. Now I hear the Millennium will spin, but you really got to force it into it. So that said, really, if you're doing a swept flying wing, reverse taper elevon is probably your best answer. How much? I don't have an answer for you there. But we do know that there's some death traps out there that you should avoid at all costs. Probably 3 of them. And these are all conventional. So the conventional answer that we use on aircraft is wrong for flying wings. This is the right answer for flying wings. For the last part of the video here, I will tell you that the reason that I put this video up on YouTube, usually all of this technical information I reserve just for my patrons on Patreon, because those are the guys that pay the money and really make this project go. But I wanted to get this information out there to try to prevent unnecessary accidents and injuries and death. There are currently, that I know of, 3 flying wing projects in Europe that don't use this. Because this is relatively new. It's in the past few years, 5 years, 6 years, something like that. And it's really just starting to gain some traction in getting used on different models and a couple of full-size aircraft now. And it's really looking like it's the better answer for flying wings. Now, on the Prano wing, they did it because this elevon, this reverse taper elevon shape, actually gives you the largest proverse yaw and helps keep your turns coordinated without having rudders. That's a big deal, big plus. So they weren't doing it for spin resistance, they were doing it for something else. But in the process, they gained spin resistance by stopping or limiting the spanwise flow. So we have limited information on it, but we do know that these are bad based on historical references. And there are 3 projects in Europe right now that use one of these 3 designs. They don't use this. And I've tried to reach out to all of them. I've had one respond. The one that responded told me that I was full of it. And, you know, it's the non-invented here syndrome. You know, I don't know you, I don't know your experience, right? They don't know that I've been at this for 50 years and that I have a master's degree in aero engineering, even though I told them all of that. That didn't carry any weight with them. I don't know, maybe I had to get a copy of my college degrees and send them to them. But they just didn't want to hear it. I suspect they didn't want to hear it because they already have molds made. Molds are extremely expensive, and their design is set up to have, I think they're on this one, I think they're on a tapered elevon. Now, I haven't heard anything about that project in a couple of years, 2.5, maybe going on 3 years. So maybe it's dead in the water. I hope their test pilot isn't dead. If they're still working on it, I'll tell you again, you need to get rid of this elevon shape. It is a death trap. There's another one that's in the works. The guy's built the fuselage, mounted the motor, he's got the wing carry through. He's basically got everything but the wings. And from the drawings that I've seen, he seems to have something between here and here. He's got an elevon out at the wingtip that looks just very conventional. And I would say, if you haven't built those wings yet, all the way done, even if you have finished them, if you finished them, throw them away. Build new wings. Get the reverse taper. And the fact that these people have flown models of these planes before they built them is meaningless. The Reynolds numbers are not the same, and as we've seen with my work, Reynolds numbers are fooler. My model flew fine. You get into full-scale Reynolds numbers, you got a problem. So, reverse taper elevon for the flying wings that are currently in work. And the third one is a group of students, and they're actually learning aero engineering hands-on. Wonderful group of students, excellent program they appear to have, and they're doing a redo of the SB-13, and it's highly improved in terms of its air elasticity and some of the aerodynamics. But they essentially have strip elevon, kind of like what you would find on a standard sailplane, and they have winglets out at the end. And I have very serious concerns for them. Even with the laminar flow airfoil, we're getting the higher momentum flow closer to the trailing edge. I think it's still going to be an issue. And I know that they've already built their wings, they've got controls in there and everything. They've flown a half-scale model, but once again, the model is not going to tell you the truth. And I would have to just a shout out to them, be extremely careful with a full-size one. Be very careful about CG location, be very careful about amount of control deflection, and man, be super careful when you're flying close to stall, because you could be very prone to stall spin due to the span-wise flow. And I know it's too late for you guys to go back and hack up the wing. You'd have to build new outer panels and completely redesign the control routing in order to do this reverse taper. But I myself, I've done dozens of flying wing designs. I would never, ever use one of these elevons ever again. Only reverse taper for my designs going forward. It really makes sense. There's three factors at work that help keep the flow attached and going chord-wise, not span-wise, and span-wise flow will kill you. So, there we go. I think that's important insights. I hope that people can use them in their own designs. I hope they will use them. You don't have to reinvent the wheel. I try not to reinvent the wheel. I try to steal from as many smart people as I can. Please steal these ideas. Go this route. Go with the reverse taper elevons. Ignore all the other answers. Don't even bother experimenting. If you want to experiment with the elevon shape, do a bunch of different reverse tapers and put up a YouTube video and tell us what works and what doesn't work, what works better. And we can all learn. But you don't have to reinvent the wheel at this point. And if you can avoid crashing your model or your full-size aircraft, that's a big plus. And that's why I put this video up, to save you the trouble and the grief of destroying another aircraft. So, there we go. I hope that my speechifying here doesn't turn around and bite me in the butt later and I crash my wing and kill myself or injure myself. Heaven forbid that happen, but we're going to proceed with the test flying very carefully. I think the reverse taper elevons are going to work like gangbusters. I'll have some more flow tests coming of the actual elevon extensions with the reverse taper showing the flow condition. So I wish you the best of luck with your projects. I hope that you've learned a little something today. And to the folks in Germany, no offense, just trying to help, not standing here in the U.S. being a know-it-all, just saying, hey, look what I stumbled across, look what I learned, and maybe you can apply it to your designs, maybe you should apply it to your designs to avoid trouble down the line. So, all of that said, I'll close as I always close. Fly safe and bye for now.